300 million light-years across, the observable universe defies our imagination. Yet everything we see begins right here. The Milky Way galaxy is our cosmic home, a majestic barred spiral structure spanning 100,000 light-years and cradling over 100 billion stars. To human senses, this swirling island of stellar nurseries, ancient white dwarfs and planets feels infinitely vast. Travelling at the ultimate speed allowed by the cosmos, a photon of light still requires 100 millennia just to journey from one edge of our galaxy to the other. Yet when placed against the grand architecture of the deeper cosmos, this immense stellar metropolis shrinks into absolute insignificance. If we were to scale the entire Milky Way down to the size of a single grain of sand, the vastness of the universe that surrounds us would stretch out wider than the entire planet Earth. Today, we will find out just how staggeringly vast the universe is compared to our own galaxy. If you are ready to venture to the absolute edge of cosmic reality, please hit the like button and subscribe to the channel to join our journey through the deep cosmos. Before we leave our galactic neighborhood behind, please take a moment to leave a comment below, telling us exactly where and at what time you are watching this video on our tiny blue planet. Now, look past the stars of our night sky and prepare to measure the true scale of the universe against the solitary galactic island we call home. To truly comprehend how the wider universe dwarfs everything we know, our journey must begin within the boundaries of our own celestial home. The Milky Way is not a chaotic cloud of gas and dust, but a highly organized, majestic, barred spiral galaxy. When astronomers look at it from a cosmic perspective, they see a massive disk with a dense central bar of ancient stars, from which several luminous arms curve outward into the darkness of space. This grand structure measures approximately 100,000 light-years from one edge to the other. To put that in perspective, a single light-year is the distance that light travels in one Earth-year, moving at the absolute universal speed limit of 186,000 miles per second. That means a single light-year is roughly 6 trillion miles long. Multiply that by 100,000, and the physical diameter of our galaxy becomes a number so utterly massive that human intuition completely fails to grasp it. Our galaxy is home to anywhere between 100 billion and 400 billion stars. Each of these stars is a sun, many of them far larger and hotter than our own, and the vast majority of them host entire families of planets, moons, and asteroid belts. If every single star in the Milky Way were counted as a single second of time, it would take more than 3,000 years of continuous counting just to name them all. This entire collection of stellar mass, gas clouds, planetary systems, and cosmic dust rotates slowly around a supermassive black hole located at the very center of the galaxy, a gravity well known as Sagittarius A star, which contains the mass of over 4 million suns. Our own solar system occupies a quiet, suburban neighborhood within this colossal disk of stars. We are located approximately 26,000 light-years away from the violent, crowded galactic center, nestled safely within a smaller structure called the Orion Arm, which sits between two of the major spiral arms, the Sagittarius and Perseus arms. From our vantage point on Earth, the rest of our galaxy looks like a milky band of pale light stretching across the night sky. A view that is actually the edge-on profile of the galactic disk viewed from the inside out. When you gaze up at that band of light, you are looking at billions of suns whose light has travelled through space for tens of thousands of years before finally striking your eyes. Even though the Milky Way is a monstrously large structure on a human scale, it is completely surrounded by vast, cold, empty space. For a long time, early astronomers believed that our galaxy was all that existed, an island universe floating completely alone in an infinite void. However, we now know that the Milky Way is just one member of a small galactic family known as the Local Group. This neighborhood consists of more than 80 recognized galaxies, most of which are tiny dwarf galaxies that act as satellites, trapped by the gravity of their larger neighbors. The undisputed heavyweight champion of our immediate cosmic neighborhood is the Andromeda Galaxy, also catalogued by astronomers as Messier 31. Located approximately 2.5 million light-years away from Earth, Andromeda is the closest large spiral galaxy to the Milky Way. When we say that it is 2.5 million light-years away, it means that the light we see from Andromeda tonight left its stars long before modern human beings ever walked the Earth. The photons hitting our telescopes today have been journeying through the freezing vacuum of space for 2.5 million years, surviving the long trek across the intergalactic void. Andromeda is even larger than the Milky Way. While our galaxy spans 100,000 light-years, Andromeda stretches across roughly 220,000 light-years, making it more than twice as wide. Astronomers estimate that Andromeda contains close to 1 trillion stars, which is significantly more than our own stellar population. If you were to look at Andromeda through a powerful telescope, you would see a spectacular, brilliant swirl of starlight that is currently rushing toward us at an incredible speed. Despite the enormous distance of 2.5 million light-years separating our two galaxies, the invisible hands of gravity are constantly pulling the Milky Way and Andromeda toward each other. The two massive structures are locked in a cosmic dance, closing the gap between them at a rate of about 70 miles per second. In approximately 4 to 5 billion years, this mutual gravitational attraction will result in a spectacular, slow-motion collision. The Milky Way and Andromeda will pass completely through each other, their massive gravitational fields ripping apart their familiar spiral structures, scattering millions of stars into new orbits and triggering waves of intense new star formation as their gas clouds compress. Eventually, over billions more years, the two separate entities will merge completely to form a single massive elliptical galaxy that astronomers have already named Milkomeda. But even when we combine the Milky Way and Andromeda into one giant cosmic structure and include all 80-plus dwarf galaxies of the local group, we have still only mapped a microscopic fraction of the broader universe. The entire local group, with all its trillions of stars and millions of light-years of empty space, is nothing more than a tiny, isolated outpost in a much larger landscape. The distance between the Milky Way and Andromeda might seem like an uncrossable gulf, but on the true scale of the cosmos, it is merely the first step outside our front door. To see just how small our galaxy really is, we must look beyond our neighbourhood and understand the vast, interconnected network that awaits us in the deep universe. To understand how our galaxy compares to the rest of the universe, we must answer a fundamental question of astrophysics. How do we know how far away everything is? Space is a vast, dark expanse, devoid of physical landmarks, and we cannot simply stretch a tape measure across the cosmos. Over centuries of intense scientific observation, humanity has constructed a metaphorical tool called the cosmic distance ladder. This ladder consists of a series of overlapping astronomical methods, where each rung builds upon the scientific accuracy of the previous one, allowing us to map distances from our nearby stellar neighbours all the way to the edge of the observable universe. Without this rigorous mathematical framework, our understanding of the universe would be flat, a two-dimensional sky with no sense of depth or true scale. The very first rung of the cosmic distance ladder relies on pure, fundamental geometry through a phenomenon known as stellar parallax. To understand parallax, you can perform a simple experiment right now. Hold one finger out in front of your face, close your left eye, and look at your finger against the background wall. Now, switch eyes, closing your right eye and opening your left. Your finger appears to shift position against the distant objects in the room, even though your hand did not move. This apparent displacement occurs because your two eyes view the finger from two slightly different vantage points. Astronomers apply this exact geometric principle to the stars on a cosmic scale. Instead of using the distance between two human eyes, they use the massive diameter of Earth's orbit around the Sun as their baseline. When astronomers observe a nearby star in January, and then look at it again 6 months later in July, the Earth has moved to the opposite side of the Sun, a distance of roughly 186 million miles. Because of this massive shift in our orbital position, the nearby star appears to move slightly against the incredibly distant background of more stable, faraway galaxies. By measuring the tiny angle of this apparent shift, known as the parallax angle, and using basic high school trigonometry, scientists can calculate the exact distance to that star with immense precision. However, stellar parallax has its limits. The farther away a star is, the smaller its parallax angle becomes. Eventually, the angle is so incredibly minuscule that even our most powerful space-based observatories cannot detect it. Parallax is perfect for mapping our local galactic neighborhood within a few thousand light-years, but to leap across the vast intergalactic voids to other galaxies, we need a stronger, more revolutionary cosmic rung. That next critical rung was discovered in the early 20th century by an astronomer named Henrietta Swan Leavitt, who was studying a specific class of pulsating stars known as Cepheid variables. These are aging massive stars that naturally expand and contract, causing their intrinsic brightness to fluctuate in a highly predictable, rhythmic cycle over days or weeks. Leavitt made a groundbreaking scientific discovery that changed astronomy forever. She realized that there is a direct, mathematically precise relationship between a Cepheid variable's period of pulsation and its true intrinsic luminosity, meaning how bright the star actually is at its source. Prior to this discovery, when astronomers looked at a bright star in the night sky, they never knew if it was actually a highly energetic, brilliant star located far away, or simply a dim, low-energy star located very close to Earth. Henrietta Swan Leavitt's period luminosity relation completely solved this cosmic puzzle. By measuring the exact time it takes for a Cepheid variable star to complete one full cycle of brightening and dimming, astronomers can immediately calculate its true intrinsic brightness. Once they know exactly how much light the star is actually emitting, they can compare that value to how bright the star appears to be from our telescopes on Earth. Because light fades across space according to a strict mathematical rule known as the inverse square law, the difference between a star's true luminosity and its apparent brightness reveals its exact distance. In the 1920s, an astronomer named Edwin Hubble used Leavitt's discovery to locate Cepheid variables inside what was then known as the Andromeda Nebula. When he calculated the distance, he shocked the scientific community by proving that Andromeda was not a cloud of gas inside the Milky Way, but an entirely independent galaxy located millions of light-years away. This single scientific insight instantly transformed our understanding of reality, shattering the idea that the Milky Way was the entire universe. Yet, even Cepheid variables have a limit. As we look deeper and deeper into the universe, individual stars inside distant galaxies eventually blur together, making it impossible to isolate a single Cepheid variable star. To climb to the next rung of the cosmic distance ladder and measure distances across billions of light-years, astronomers rely on an incredibly violent cosmic event known as a Type 1a supernova. This specific type of supernova occurs in a binary star system containing a white dwarf, which is the dead, dense core of a star that was once like our Sun. The white dwarf slowly siphons matter away from its companion star, accumulating layers of hydrogen and helium gas over millions of years. However, a white dwarf cannot grow indefinitely. Physics dictates that once a white dwarf reaches a very specific mathematical mass limit, exactly 1.44 times the mass of our Sun, a threshold known as the Chandrasekhar limit, it can no longer support its own weight. The moment the white dwarf hits the Chandrasekhar limit, its core undergoes a runaway catastrophic thermonuclear explosion. Because every single Type 1a supernova explodes at exactly the same mass threshold, they all unleash the exact same colossal amount of energy and light. In the field of astrophysics, these predictable explosions are called standard candles. They act like universal light bulbs of a known wattage scattered across the deep cosmos. When a Type 1a supernova detonates in a galaxy halfway across the observable universe, it shines with such an immense, blinding brilliance that it can briefly outshine all the hundreds of billions of stars in its host galaxy combined. Astronomers can spot these brilliant flashes of light across incomprehensible distances by measuring the maximum apparent brightness of the supernova as its light reaches Earth and comparing it to the fixed, known intrinsic luminosity of the Chandrasekhar explosion. Scientists can determine exactly how many billions of light-years away the host galaxy is. It was the precise measurement of these distant Type 1a supernovae in the late 1990s that led to another revolutionary scientific breakthrough: the discovery that the expansion of the universe is not slowing down under the weight of gravity, but is actually accelerating over time. This continuous chain of measurement from the simple geometry of stellar parallax, through the pulsing rhythm of Cepheid variables, to the blinding explosions of Type 1a supernovae, provides the empirical foundation for our cosmic geography. We do not guess how massive the universe is compared to the Milky Way, we calculate it using the ironclad laws of physics. Each method connects with the next, proving that the vast distances separating our galaxy from the rest of space are real, measurable, and stunningly immense. Armed with the cosmic distance ladder, astronomers began to push past the boundaries of the local group, revealing that the universe does not merely consist of isolated galaxies drifting aimlessly through a void. Instead, gravity organizes galaxies into immense, hierarchical structures that make the Milky Way look like a microscopic speck. When we zoom out from our immediate neighborhood, we find that the local group is just a small suburban component of a much vaster assembly known as the Virgo Supercluster. A supercluster is a massive collection of galaxy clusters and individual galaxies bound together by mutual gravitational attraction, representing some of the largest structures in the known universe. The heart of our local supercluster is the Virgo cluster itself, a monstrously dense gravitational powerhouse located approximately 54 million light-years away from Earth. Unlike our modest local group, which contains only a few large spiral galaxies, the Virgo cluster alone contains well over 1,300 confirmed galaxies, and possibly as many as 2,000. The gravitational pull exerted by this massive concentration of stellar systems is so immensely powerful that it influences the motion of every single galaxy around it, including our own. The Milky Way, along with Andromeda and the rest of the local group, is being actively drawn toward the Virgo cluster in a grand cosmic journey known as the Virgo infall. We are falling through space toward this dense galactic core at a speed of hundreds of miles per second, experiencing the relentless pull of a collective gravitational well that spans millions of light-years across. The Virgo Supercluster, which encompasses both the dense Virgo cluster and our own local group, stretches across an impressive diameter of approximately 110 million light-years. For decades, scientists believed that this massive structure was the absolute limit of cosmic organization, the largest definitive boundary we could draw around our place in space. They assumed that beyond the Virgo supercluster, the universe simply smoothed out into an endless, uniform repetition of similar superclusters separated by empty space. However, in the year 2014, a team of cosmologists led by Brent Tully mapped the velocities of thousands of galaxies in our local universe, looking not just at where galaxies are located, but at how they are moving through space. By subtracting the uniform expansion of the universe from the actual movements of these galaxies, the scientists isolated their peculiar velocities, which are the motions driven purely by the gravitational pull of massive cosmic structures. The resulting data revealed a groundbreaking, revolutionary map of our wider cosmic reality. The Virgo supercluster was not an independent, self-contained structure at all. Instead, it was merely one small branch, a single minor tributary, belonging to a gargantuan, previously unknown cosmic watershed of galaxies. The scientists named this colossal structure Laniakea, a term that translates to immeasurable heaven in the Hawaiian language. Laniakea is a mind-bogglingly vast supercluster system that spans more than 500 million light-years from one end to the other. It defines the absolute boundaries of our cosmic home on a truly grand scale, containing an estimated 100,000 large galaxies and countless smaller dwarf systems. Within Laniakea, the distribution of matter is not uniform. Galaxies do not sit still. They flow along invisible gravitational pathways, like water trickling down valleys toward a central basin. Every single galaxy within the boundaries of Laniakea is moving toward a specific, incredibly massive gravitational anomaly known as the Great Attractor. The Great Attractor is a mysterious, dense concentration of mass located roughly 150 million light-years away from us, sitting in a region of the sky shrouded by the thick gas and dust of our own galactic disk, an area astronomers call the zone of avoidance. Because this dust blocks our view of visible light, scientists had to use X-ray and radio astronomy to peer through the galactic plane, discovering a massive collection of galaxy clusters known as the Norma cluster and the Regina cluster, pulling everything toward them. The Milky Way, the Andromeda galaxy, the entire Virgo cluster, and all the surrounding galactic structures within the 500 million light-year expanse of Laniakea are caught in this titanic gravitational current, rushing toward the great attractor at speeds exceeding 1 million miles per hour. When we view Laniakea as a whole, its visual shape resembles a delicate, fibrous feather or a complex neural network glowing in the dark expanse of space. The outer boundaries of Laniakea are defined by the points where the gravitational flows split. On one side of the boundary line, galaxies flow toward the great attractor. On the other side, they are pulled toward entirely different cosmic watersheds, such as the neighbouring Perseus-Pisces supercluster. If we scale the entire Laniakea supercluster down so that it fits across the width of a standard television screen, the entire Milky Way galaxy becomes completely invisible to the naked eye. Our home galaxy, with its 400 billion suns, its majestic spiral arms, and its entire history of human observation, becomes nothing more than a fraction of a pixel, an infinitesimal pinpoint of light drifting along a massive cosmic highway of gravity. This is the power of viewing the universe across progressively larger scales. We cannot truly understand how large the cosmos is compared to the Milky Way by looking at our galaxy in isolation. We must see it as a tiny participant in a grand, interconnected network. The sheer physical scale of Laniakea demonstrates that our galaxy is not a dominant force in the cosmos, but a minute component of a massive architectural masterpiece. Yet even as we stand back to admire the gargantuan scale of Laniakea, modern astrophysics reminds us that we are still looking at our local neighbourhood. Laniakea is massive, but it represents just a tiny fraction of the broader universe. Beyond the outer edges of this immeasurable heaven lie even grander structures, separated by terrifying expanses of absolute nothingness, waiting to challenge our understanding of space and time. To appreciate the true scale of the cosmos compared to the Milky Way, we must look beyond individual superclusters like Laniakea and observe the entire universe on its grandest possible scale. When we zoom out hundreds of millions of light-years, individual galaxies blur together, and a breathtaking architectural marvel emerges from the darkness. Matter in the universe is not scattered randomly like dust across a room, nor is it concentrated in a single central point. Instead, it is organized into a colossal three-dimensional web known to modern astrophysics as the cosmic web. This network is the largest known structure in existence, a definitive blueprint of matter that defines the shape of our universe across billions of light-years. The cosmic web consists of three distinct components: dense nodes, elongated filaments, and massive voids. The nodes are the crowded intersections of the web, where multiple cosmic pathways meet. These nodes are formed by massive clusters of galaxies, packed tightly together by intense gravitational forces, creating the brightest and most energetically active hubs in the universe. Radiating outward from these dense nodes are the cosmic filaments, which serve as the highway systems of the grand cosmic design. These filaments are incredibly long, thin ribbons of dark matter, hot intergalactic gas, and millions of galaxies threaded together across space. They stretch over hundreds of millions of light-years, acting as bridges that transport matter and pull isolated galaxies toward the crowded nodes. The Milky Way, along with the rest of the Laniakea supercluster, is embedded within one of these delicate filaments, riding along a cosmic current of matter that spans the deep, dark vacuum. However, the most shocking realization for astronomers mapping the cosmic web was not the presence of these massive filaments, but the terrifying amount of empty space that sits between them. The vast majority of the volume of the universe does not contain stars, planets, or galaxies. Instead, it is occupied by gargantuan expanses of absolute nothingness, known as cosmic voids. These voids are immense, roughly spherical regions of space that contain almost no visible matter whatsoever. While a typical region of space within a filament is crowded with thousands of galaxies, a cosmic void is a barren wasteland, a silent vacuum where the density of matter is less than 1/10 of the universal average. The cosmic voids are formed through a process of gravitational runaway that began shortly after the Big Bang. In the infant universe, matter was distributed almost perfectly evenly, but tiny subatomic fluctuations created regions that were slightly denser than others. Over billions of years, these slightly denser regions exerted a stronger gravitational pull, drawing matter away from the less dense areas. The filaments and nodes grew thicker and more massive, while the less dense regions were systematically emptied of their contents, hollowed out by the surrounding gravity, until they became the gargantuan voids we observe today. Galaxies located near the edges of these voids are continuously pulled outward toward the massive filaments, effectively evacuating the interior of the void and leaving behind nothing but pure, unadulterated vacuum. The physical scale of these cosmic voids completely dwarfs our galaxy in a way that challenges human comprehension. Consider the Boötes Void, often referred to by astronomers as the Great Nothing. Discovered in the late 20th century, the Boötes Void is one of the largest known voids in the entire observable universe. It is a terrifying expanse of empty space, measuring approximately 330 million light-years in diameter. To put that into perspective, the physical diameter of the Boötes Void is more than 3,000 times larger than the entire width of the Milky Way galaxy. If our home galaxy were placed dead center inside the Boötes Void, humanity would have believed that we were completely alone in the cosmos. The night sky from Earth would have been pitch black, devoid of any visible stars or neighboring galaxies. We would not have discovered the existence of other galaxies until the development of highly advanced telescopic technology, capable of peering across hundreds of millions of light-years to see the distant glowing walls of the cosmic web. Astronomers estimate that within the entire 330 million light-year volume of the Boötes Void, only about 60 isolated galaxies have ever been detected. In a normal region of the cosmic web of equivalent size, there would be tens of thousands of large galaxies, each containing hundreds of billions of suns. The galaxies trapped inside the Boötes Void are cosmic outcasts, drifting in total isolation, separated from the rest of the universe by expanses of nothingness so wide that light itself takes hundreds of millions of years to cross them. They represent a stark contrast to our own galactic environment, showing us just how crowded our local filament is, yet highlighting the vast scale of the empty space that surrounds us. When we view the cosmic web as a whole, it resembles a complex organic foam or a vast neural network glowing faintly against an eternal night. The Milky Way is a microscopic participant in this grand design. If you could step completely outside the cosmic web and look at a section of the universe spanning 10 billion light-years, the majestic spiral arms of our galaxy, the supermassive black hole at our center, and all our hundreds of billions of suns would disappear entirely. The Milky Way would not even register as a single pixel of light. It would be an invisible subatomic speck trapped inside a thin filament, which is itself just a minor thread woven into the fabric of a massive wall of galaxies surrounding an ocean of absolute nothingness. The science of the cosmic web proves that our universe is defined not by the matter it contains, but by the vast spatial architecture that separates that matter. This progression across cosmic scales underscores that the Milky Way is not an isolated ruler of the cosmos, but a tiny molecule in a grand flowing intergalactic river. As we continue to climb the cosmic distance ladder and look further into the distance, we realize that the cosmic web we have mapped is only the part we can see. The physics of light and the history of time itself impose a strict boundary on our observations, forcing us to confront the true physical limits of our reality. The boundary of the observable universe. To confront the true scale of the universe compared to the Milky Way, we must transition from mapping local galactic filaments to exploring the absolute physical boundary of our observational reality. This boundary is known as the observable universe. It represents a spherical bubble of space, centered precisely on Earth, encompassing every single photon of light, particle of matter, and cosmic structure that has had enough time to travel to our telescopes since the beginning of time itself. Beyond this boundary lies the unobservable universe, a vast realm whose light has simply not reached us yet, remaining permanently hidden from our sight. Our understanding of this grand cosmic boundary begins with the oldest light in existence, a phenomenon known to astrophysics as the cosmic microwave background radiation. Shortly after the Big Bang, the universe was a blindingly hot, dense plasma of electrons, protons, and highly energetic photons. This infant universe was so completely opaque that light could not travel through it. Photons were constantly colliding with free electrons, trapped in a chaotic, luminous fog. This state endured for approximately 380,000 years, until a monumental cosmic turning point occurred, an era known as recombination. During this epoch, the expanding universe cooled down to a temperature of roughly 3000 Kelvin, allowing electrons to finally bind with protons to form the very first stable atoms of hydrogen and helium. With the free electrons locked away inside neutral atoms, the cosmic fog instantly cleared, and the universe became transparent for the very first time. The trapped photons were suddenly liberated, bursting forth in all directions and embarking on a journey across space that has lasted for billions of years. This ancient light has been travelling through the vacuum ever since, acting as a pristine snapshot of the infant universe. As the space through which these photons travelled continued to expand over cosmic time, the wavelength of the light was stretched, shifting from highly energetic visible light down into the cooler, invisible microwave region of the electromagnetic spectrum. Today, this light bathes the entire universe in a uniform, faint glow that astronomers can detect using specialized space-based telescopes. The cosmic microwave background radiation represents the ultimate wall of time in our universe. When we peer deep into space, we are looking backward through time due to the finite speed of light. Looking at a galaxy 1 billion light-years away means we see it as it existed 1 billion years ago. By looking as far back as physically possible, our instruments strike the cosmic microwave background radiation, capturing the image of the universe when it was only 380,000 years old. It is the absolute horizon of our visible reality, a luminous background curtain behind which the Big Bang itself remains hidden. The discovery and mapping of this ancient radiation led directly to an extraordinary scientific paradox regarding the physical size of the observable universe. If the universe began exactly 13.8 billion years ago, a basic understanding of physics might suggest that the farthest distance we could possibly see would be exactly 13.8 billion light-years. According to this logic, light travelling at the speed of light, limit for 13.8 billion years, could only cover a maximum distance of 13.8 billion light-years. However, when cosmologists measure the actual physical radius of the observable universe today, they discover that it does not measure 13.8 billion light-years at all. Instead, the true radius of the observable universe stretches out to an astonishing 46.5 billion light-years in every direction, creating a total diameter of 93 billion light-years. This jaw-dropping discrepancy creates what appears to be a massive scientific paradox. How can the radius of the observable universe be more than 3 times larger than the distance light could travel during the entire age of the universe? The answer to this cosmic riddle lies in a fundamental principle of Albert Einstein's general theory of relativity: the expansion of space itself. Space is not a fixed, rigid stage upon which cosmic events unfold. Instead, space is a dynamic, flexible fabric that can stretch, expand, and bend over time. The Big Bang was not an explosion of matter outward into an existing empty room. It was the sudden, rapid expansion of space itself. To resolve the paradox, we must understand that while a photon of light has been travelling toward Earth for 13.8 billion years, the empty space behind that photon has been continuously stretching out during its entire journey. Imagine a cosmic ant walking along a rubber band toward your hand, at a constant speed of 1 inch per second. If the rubber band is 10 inches long, it should take the ant exactly 10 seconds to reach your hand. However, if you actively stretch the rubber band while the ant is walking, the distance the ant has already covered stretches out behind it, and the distance remaining in front of it increases as well. When the ant finally reaches your hand after a long struggle, the total length of the rubber band will be far greater than the original 10 inches. This is exactly what happens to light travelling across the expanding cosmos. The ancient stars and gas clouds that emitted the cosmic microwave background radiation 13.8 billion years ago were much closer to our position at the time of emission. But as those photons travelled through space toward the region that would eventually become the Milky Way, the space they traversed expanded continuously. By the time those photons finally strike our satellite detectors today, the actual physical point in space where that light originated has been pushed far away from us by the relentless stretching of the cosmic fabric. Today, that original source point sits at a calculated distance of exactly 46.5 billion light-years away from Earth. This reality completely redefines the scale of our galaxy. The Milky Way, spanning its 100,000 light-years, is trapped inside a colossal sphere that stretches 93 billion light-years from side to side. To contrast these numbers mathematically, we must understand the volume of this space. The volume of a sphere increases with the cube of its radius. When you calculate the volume of a sphere with a radius of 46.5 billion light-years and compare it to the volume of the disk of the Milky Way, the results are staggering. The observable universe is so incredibly massive that it can easily hold hundreds of billions of individual galaxies of our size. If you were to take the entire Milky Way galaxy, with all its 400 billion suns, its nebulae, its planets, and its supermassive black hole, and try to use it to fill the volume of the observable universe, it would be equivalent to dropping a single microscopic drop of water into a massive Olympic-sized swimming pool. Our entire galaxy is nothing more than a faint whisper in a thunderous cosmic symphony. Every star system we have ever mapped, every constellation that has guided human sailors for millennia, and every deep space image captured by our most advanced instruments represents a microscopic fraction of this 93 billion light-year bubble. Furthermore, this 46.5 billion light-year horizon, known scientifically as the particle horizon, represents a strict limit on what humanity can ever know about the cosmos. Because no information, force, or signal can travel faster than the speed of light, we are completely cut off from whatever exists beyond this cosmic wall. If there are massive clusters of galaxies, cosmic structures, or entirely different configurations of matter sitting 47 billion light-years away, their light has simply not had enough time to cross the expanding universe to reach us. They are completely outside our causal reality. When we contemplate the scale of the observable universe, we are looking at the absolute boundary of human science, a vast arena where the laws of physics, the finite speed of light, and the expansion of space conspire to limit our vision. Yet the most profound realization of modern astrophysics is that this colossal 93 billion light-year bubble is not the end of existence. It is merely the limit of our sight. To understand what drives this expansion and what holds this entire structure together, we must look at the invisible forces that dominate the cosmic web, forces that human eyes can never directly see. To understand the grand architecture of the observable universe and how it compares to the Milky Way, we must investigate the invisible foundation that holds these massive cosmic structures together. When we look at deep space images of our galaxy, we see a beautiful, luminous disk of billions of stars spinning gracefully around a central hub. It looks like a self-contained, stable system governed by the standard laws of gravity that we observe on Earth. However, when astrophysicists began to apply the rigorous mathematics of orbital mechanics to the rotation of galaxies, they discovered a profound scientific mystery that shattered our understanding of cosmic matter. The visible matter within the Milky Way is completely insufficient to explain why the galaxy stays together, revealing the existence of a massive, invisible entity known as dark matter. The discovery of this invisible cosmic glue traces back to the mid-20th century and the pioneering work of an American astronomer named Vera Rubin. Rubin was conducting detailed scientific observations of the rotation curves of spiral galaxies, mapping the speeds at which stars orbit around their galactic centers at varying distances from the core. According to Isaac Newton's laws of gravitation and the later refinements of Albert Einstein's general relativity, the orbital speed of a star should depend directly on the amount of mass contained within its orbit. Because the vast majority of a galaxy's visible mass, stars, gas clouds, and dense dust, is highly concentrated near the bright galactic center, physics predicted that stars near the outer edges of the spiral arms should move much more slowly than stars located near the core, just as the distant planets in our solar system orbit the Sun at a fraction of the speed of the inner rocky planets. However, when Vera Rubin plotted the actual observational data, she discovered a completely flat rotation curve. The stars located at the extreme, dark, outer rim of the galaxy were moving at almost the exact same high velocity as the stars situated deep within the crowded galactic interior. This scientific observation presented a terrifying paradox for modern physics. According to the laws of gravity, if the outer stars are moving that incredibly fast, the limited gravitational pull generated by the visible stars and gas clouds would be completely incapable of holding on to them. At those extreme velocities, the centrifugal force should violently tear the galaxy apart, scattering hundreds of billions of suns outward into the intergalactic void, like water flying off a spinning bicycle tire. Yet, the Milky Way and trillions of other spiral galaxies have maintained their stable, elegant structures for more than 10 billion years. This realization forced scientists to conclude that there must be an immense, undetected source of mass, providing the extra gravitational pull needed to hold the galaxies together. This invisible mass does not emit, absorb, reflect, or interact with light or any other form of electromagnetic radiation in any way. It is completely transparent, passing through normal matter like a ghost, remaining entirely invisible to our optical, infrared, X-ray and radio telescopes. Because of this complete lack of electromagnetic interaction, scientists named this mysterious substance dark matter. It can only be detected indirectly through its intense gravitational influence on the visible matter that surrounds it. Subsequent cosmological measurements have revealed that dark matter is not just a minor anomaly within our galaxy. It is the dominant form of matter in the universe. When scientists calculate the total mass-energy budget of the cosmos, they discover that normal matter, everything we can see, touch, and detect, including every star, planet, gas cloud, black hole, and human being, accounts for a meager 5% of the universe. In stark contrast, dark matter makes up roughly 27% of the cosmic architecture. The remaining 68% is composed of a completely different cosmic force, known as dark energy. This means that more than 85% of all the actual physical matter in existence is completely invisible to human eyes and instruments. On a galactic scale, the Milky Way is embedded within a gargantuan, roughly spherical bubble of dark matter, known as a dark matter halo. This invisible halo is vastly larger and more massive than the visible stellar disk we call home. While the luminous stars of the Milky Way span approximately 100,000 light-years across, the surrounding dark matter halo stretches out into the intergalactic void for hundreds of thousands of light-years in every direction, enveloping our galaxy in an invisible gravitational embrace. The visible spiral galaxy we see is merely a tiny luminous island sitting at the absolute center of a massive ocean of dark matter. To visualize how dark matter shapes the wider universe compared to our galaxy, we must look at how it behaves on a macro scale across billions of light-years. Dark matter acts as the primary architectural scaffolding of the entire cosmic web. During the infant stages of the cosmos, immediately following the era of cosmic inflation, dark matter was the first substance to come together under the influence of gravity. Because it does not interact with light, it was unaffected by the intense radiation pressure that kept normal matter scattered in a hot, smooth plasma. The dark matter collapsed into a vast, intricate network of long, invisible filaments and massive spherical nodes across the expanding fabric of space. Once these massive, invisible structures were established, their immense gravitational fields acted as cosmic traps for normal matter. As the universe cooled down after the Big Bang, normal gas clouds of hydrogen and helium were pulled inexorably into the pre-existing gravitational wells created by the dark matter filaments. Inside these invisible cosmic trenches, the gas compressed, heated up, and eventually ignited to form the very first stars, proto-galaxies, and massive stellar clusters. Every single galaxy in the observable universe, including the Milky Way, was born within a cradle of dark matter. Without the gravitational framework provided by this invisible scaffolding, normal matter would have remained scattered too thinly across the expanding cosmos to ever coalesce into complex structures, meaning stars, planets, and life itself could never have formed. When we observe the interactions between entire clusters of galaxies, the true scale and power of dark matter become even more apparent. In massive structures like the Virgo cluster, hundreds of galaxies rush around a shared center of mass at velocities exceeding millions of miles per hour. The visible mass of these galaxies is far too small to keep them bound together. Without the immense gravitational mass of dark matter filling the intergalactic space between them, the clusters would instantly dissolve. Astronomers can map the exact distribution of this invisible dark matter by observing a phenomenon called gravitational lensing, which occurs when the massive gravity of dark matter bends and distorts the paths of light, travelling from even more distant galaxies behind it, acting as a giant cosmic magnifying glass. This progression across cosmic scales places the Milky Way in a completely new perspective. Our galaxy is not an independent, self-sustaining structure drifting through an empty void. It is a tiny passenger riding on an invisible highway system. The 400 billion stars we see are merely the foam on the crest of a massive, unseen dark matter wave that spans the entire 93 billion light-year bubble of the observable universe. We are completely surrounded by and dependent upon a cosmic ghost that dictates the motion of our sun and the fate of our entire galaxy, proving that the true scale of the cosmos is defined by things we cannot see. While dark matter acts as the invisible cosmic glue pulling galaxies together, an even more mysterious and dominant force works continuously to tear the grand architecture of the universe apart. This force is known to modern astrophysics as dark energy, and it constitutes approximately 68% of the total mass energy budget of the entire cosmos. If dark matter is the architectural scaffolding holding our galactic home in place, dark energy is the relentless, invisible current expanding the very fabric of space beneath our feet. To comprehend the true scale of the universe compared to the Milky Way, we must examine how this repulsive energy drives the acceleration of the universe and how it will ultimately dictate the terrifying future of our night sky. Our scientific understanding of this expanding reality began in the early 20th century with the pioneering work of an American astronomer named Edwin Hubble. By utilizing the cosmic distance ladder, specifically the period luminosity relationship of Cepheid variable stars, discovered by Henrietta Swan Leavitt, Hubble began measuring the distances to remote galaxies outside the Milky Way. At the same time, he analyzed the light coming from these distant stellar systems using spectroscopy, which splits starlight into its component colors like a prism. Hubble noticed that the light from almost every single distant galaxy was systematically shifted toward the red end of the electromagnetic spectrum, a phenomenon known as redshift. In physics, redshift occurs due to the Doppler effect when a source of waves moves away from an observer, causing the wavelengths to stretch out. Hubble made a monumental scientific discovery when he plotted the distances of these galaxies against their respective redshifts. He formulated what is now known as the Hubble-Lemaitre law, which states that the velocity at which a distant galaxy recedes from Earth is directly proportional to its distance from Earth. In simple terms, the farther away a galaxy is from us, the faster it appears to be rushing away into the deep dark vacuum. Crucially, this does not mean that the Milky Way is at the center of a cosmic explosion. Instead, it proves that the fabric of space itself is expanding uniformly in all directions. Galaxies are not rocket ships flying through a static room. They are like buttons sewn onto a stretching sheet of rubber, moving apart because the underlying fabric is expanding. For decades, cosmologists assumed that the collective gravitational pull of all the normal matter and dark matter in the universe would act as a cosmic brake, slowly decelerating this expansion over time. They believed the universe would either eventually stop expanding and collapse back down in a catastrophic big crunch, or simply slow to a gentle coasting expansion. However, in the late 1990s, two independent teams of astronomers shattered these assumptions by measuring the distances to highly remote Type 1a supernovae. Because these exploding white dwarfs act as standard candles of known intrinsic brightness, scientists could calculate exactly how fast the universe was expanding billions of years ago compared to today. The observational data revealed a stunning scientific paradox. The expansion of the universe is not slowing down under the weight of gravity at all. Instead, it is actively speeding up, expanding faster and faster with every passing second. To explain this mysterious cosmic acceleration, scientists had to invoke a completely unknown, repulsive pressure inherent to the vacuum of space itself, which they named dark energy. Unlike matter, which dilutes and weakens its gravitational pull as the universe grows larger, dark energy behaves as a constant property of space. As the universe expands and creates more empty space, more dark energy emerges to fill that space, maintaining a constant energy density that continuously pushes the universe outward at an accelerating rate. The mathematical implications of this acceleration completely redefine the scale and future of the Milky Way. At the current rate of cosmic expansion, described by the Hubble constant, space is stretching out across the entire 93 billion light-year bubble of the observable universe. On a local scale, the intense gravitational attraction of normal matter and dark matter is strong enough to overcome this expansion. Within our local group, the Milky Way and the Andromeda Galaxy are locked in a tight gravitational embrace, completely immune to the pulling force of dark energy. They will continue their dance and eventually merge into a single massive galaxy. However, on a macro scale across billions of light years, the empty intergalactic space between distant galaxy clusters is far too wide for gravity to win the battle. In these vast cosmic voids, dark energy reigns supreme. The space separating our local group from the distant filaments of the cosmic web is stretching so rapidly that the vast majority of the galaxies in the observable universe are already receding from us at an incredible speed. As time moves forward, this recession will only accelerate. The farther a galaxy is pushed away by dark energy, the faster the space between us expands. Eventually, the expansion velocity of the space separating our galaxy from distant cosmic structures will exceed the absolute speed of light limit. This does not violate Albert Einstein's special theory of relativity, which states that no object can travel through space faster than the speed of light. General relativity clarifies that space itself can expand at any speed it desires. When the space between the Milky Way and a remote galaxy expands faster than 186,000 miles per second, the photons of light emitted by that galaxy can no longer bridge the widening gulf. The light will struggle eternally against the expanding fabric, never reaching our telescopes on Earth. The distant galaxy will cross an invisible boundary known as the cosmological event horizon, permanently disappearing from our causal universe. This reality paints a terrifying picture for the long-term future of our night sky and our understanding of the cosmos. Right now, humanity lives in a privileged cosmic epoch where the cosmic web is still visible, allowing us to map Laniakea, the Boötes Void, and the cosmic microwave background radiation. But as dark energy continues to accelerate the expansion of space over the next tens of billions of years, every single galaxy cluster outside our immediate local neighborhood will be swept away past our cosmological horizon. One by one, the brilliant lights of the deep universe will dim and vanish into the eternal dark. Eventually, the universe will enter an era of total cosmic isolation. In approximately 100 billion years, any intelligent civilizations evolving on the stars of the merged Milky Way Andromeda Galaxy will look out into the night sky and see absolute unbroken nothingness beyond their own stellar boundaries. The vaster structures we talk about today, the Virgo cluster, the filaments of the cosmic web, the grand architecture of Laniakea, will have been pushed so incredibly far away that their light can never return. Future astronomers will have no empirical way to discover that other galaxies exist, nor will they be able to detect the cosmic microwave background radiation, which will be stretched into infinitely long, undetectable radio wavelengths. They will be trapped on a solitary galactic island, completely convinced that their galaxy is the entire universe, surrounded by an infinite, dead void. The effects of dark energy across cosmic scales proves that the universe is not a static museum, but a vanishing masterpiece. The 93 billion light-year bubble we occupy is actively slipping away from us. When compared to this dynamic, accelerating cosmos, the Milky Way is a tiny raft caught in an unstoppable cosmic torrent. The scale of the universe is not just vast in terms of physical distance. It is a fleeting expanse of time and space driven by a dark pressure that is systematically erasing the cosmic architecture, leaving our home galaxy completely isolated in cold, expanding darkness. To comprehend the true expanse of the universe relative to the Milky Way, we must examine the advanced technological instruments that allowed humanity to pierce the intergalactic dark. For the vast majority of human history, our view of the cosmos was constrained by the thick, turbulent atmosphere of Earth, which distorts starlight and absorbs critical wavelengths of light. We were like deep-sea divers looking up at the sky through muddy water. This limitation kept our understanding of the universe flat and small, leaving us completely unaware of the true scale of the deep cosmos. The dawn of the era of space-based observatories completely shattered this observational ceiling, allowing us to deploy incredible machines directly into the freezing vacuum of space. The pioneer of this technological revolution was the Hubble Space Telescope, launched into low Earth orbit in the late 20th century. By operating completely above the atmospheric distortion, Hubble captured images of the universe with unprecedented clarity and precision. In the mid-90s, the director of the Space Telescope Science Institute, Robert Williams, decided to perform a daring and highly controversial scientific experiment. He decided to point the incredibly valuable space telescope at a tiny, completely empty patch of the sky near the constellation Ursa Major. This patch of sky was chosen precisely because it contained absolutely nothing of interest. No bright nearby stars, no known gas clouds, and no mapped galaxies within the Milky Way. It was a region of absolute pitch-black void. For 10 consecutive days, the Hubble Space Telescope stared unblinkingly into this single point of darkness, executing hundreds of separate exposures to accumulate every single stray photon of light that had travelled across the vast cosmos. The resulting image, known as the Hubble Deep Field, completely shocked the global scientific community and fundamentally transformed our understanding of cosmic reality. The patch of sky, which was so incredibly small that it could be completely covered by a single grain of sand held at arm's length, was not empty at all. Inside that tiny sliver of darkness, Hubble revealed more than 3,000 distinct galaxies, crowded together in a breathtaking tapestry of light. Each of those 3,000 pinpoints of light was an independent galaxy, many of them far larger than the Milky Way, containing hundreds of billions of suns, planetary systems, and cosmic structures. Because of the finite velocity of light, the Hubble Deep Field was not just a map of space, it was a profound window into the deep past. The light from the smallest, most distant red smudges in the image had travelled across the expanding universe for more than 12 billion years before striking the telescope's digital detectors. Hubble was looking backward through time, capturing images of these stellar metropolises as they existed when the universe was in its absolute infancy. This single scientific observation proved that the universe was packed with hundreds of billions of galaxies, instantly shrinking the Milky Way into a single drop in an infinite planetary ocean. As technology advanced into the 21st century, astrophysics required a new, even more powerful tool to look even deeper into the primordial dark. The answer was the James Webb Space Telescope, a monumental feat of engineering positioned roughly 1 million miles away from Earth, at a stable gravitational point known as the second Lagrange point. While the Hubble Space Telescope observes the universe primarily in visible and ultraviolet light, James Webb was designed as a highly sensitive infrared observatory. This technological transition was critical because of the continuous expansion of the universe driven by dark energy. As light travels across billions of light years of expanding space, its wavelength is actively stretched out, shifting from visible light into the longer, invisible infrared wavelengths of the electromagnetic spectrum, a process known as cosmological redshift. To see the absolute first generation of stars and galaxies that formed after the Big Bang, we must look in the infrared spectrum. Furthermore, infrared light possesses the unique physical capability to pass completely through the dense, opaque clouds of cosmic dust that fill our galaxy, allowing us to peer into stellar nurseries and galactic cores that were previously hidden from human sight. James Webb possesses a massive primary mirror measuring 21.3 feet across, composed of 18 hexagonal segments coated in a microscopic layer of pure gold, which is the perfect material for reflecting infrared light. To maintain the extreme sub-zero temperatures required to detect faint infrared heat signals from the edge of time, the telescope is shielded by a massive 5-layer sunshield the size of a tennis court. When the James Webb Space Telescope released its very first deep field image, known as First Deep Field, it focused on a massive cluster of galaxies called SMACS 0723. The immense gravitational mass of this cluster acts as a gravitational lens, bending and magnifying the light from even more distant galaxies situated directly behind it, acting as a natural cosmic telescope. The resulting image revealed thousands of spectacular ancient galaxies, glowing with immense clarity. The gold-coated mirror of James Webb captured the light of galaxies that existed more than 13.1 billion years ago, just a few 100 million years after the Big Bang itself. These deep space images reveal a stark scientific truth about the development of the universe across cosmic scales. When we look at the most distant galaxies captured by James Webb, we are observing the universe at a time when the Milky Way did not even exist. We are witnessing the chaotic, energetic building blocks of the cosmos, small, irregular proto-galaxies actively colliding and merging together to eventually form the large, structured spiral systems we see today. The light hitting the golden mirrors of James Webb today left its source long before the Earth formed, long before our Sun ignited, and long before the gas clouds of our local neighbourhood coalesced into the Milky Way disk. By utilising these space telescopes, humanity has effectively transformed the night sky into a profound geological record of time and space. We can look at a single image and see galaxies at varying stages of evolutionary history, ranging from ancient, highly developed elliptical systems nearby to young, violent starburst galaxies at intermediate distances, all the way to the primitive, faint red sparks of the infant universe at the absolute edge of our vision. This observational capability completely redefines the scale of our home galaxy. The Milky Way is merely a modern inhabitant of an ancient, ongoing cosmic narrative that stretches back 13.8 billion years. The data gathered by the Hubble and James Webb telescopes prove that our galaxy is not the centre of existence, nor is it a unique anomaly. It is one of an estimated 2 trillion galaxies that populate the 93 billion light-year bubble of the observable universe. Every single time we point our most advanced telescopes at a patch of absolute darkness, the universe responds by revealing thousands of unseen galaxies, pushing the boundaries of our knowledge further into the deep, dark vacuum. The era of space telescopes has shown us that the scale of the cosmos is limited only by our ability to build windows into the dark, proving that the vastness that surrounds our galaxy is real, measurable, and filled with infinite wonders. To comprehend the ultimate scale of the universe relative to the Milky Way, we must look beyond the 46.5 billion light-year wall of our observable bubble and confront the absolute physical nature of the entire unobservable cosmos. This brings us to the ultimate scientific frontier, the geometry, origin, and shape of space itself. While our telescopes are permanently limited by the distance light could travel since the Big Bang, the laws of physics and mathematics allow us to analyse the grand curvature of the universe, providing structural clues about the infinite expanse that lies hidden far beyond our sight. The scientific investigation into the true shape of the universe depends entirely on a fundamental concept in cosmology, known as the critical density. According to the mathematics of Albert Einstein's general theory of relativity, the geometry of space is dictated by the precise balance between the total amount of matter and energy it contains and the outward expansion rate of the cosmos. The critical density represents the exact mathematical threshold where the gravitational pull of all the normal matter, and dark energy perfectly balances the cosmic expansion. If the actual density of the universe is greater than this critical value, the intense collective gravity will cause the fabric of space to curve inward on itself like a sphere. This is known as a closed universe, a three-dimensional geometry where if you travel in a straight line long enough, you will eventually loop back to your exact starting point, meaning space is finite yet has no boundary. If the actual density is less than the critical threshold, space will curve outward in the opposite direction, creating an open universe with a hyperbolic geometry shaped like a colossal horse saddle. In this scenario, parallel lines will diverge over time, and space stretches out infinitely in all directions. However, when astronomers utilize advanced satellite observatories to measure the temperature fluctuations of the cosmic microwave background radiation with immense precision, they discover something truly extraordinary. The actual density of our universe matches the critical density with an error margin of less than 1%. This precise balance indicates that the universe is geometrically flat. A flat universe means that Euclid's classical geometry works perfectly across billions of light years. Parallel lines stay parallel forever, and the angles of a massive cosmic triangle will always add up to exactly 180 degrees. The mathematical implication of a perfectly flat universe is staggering for the overall scale of our reality. While a closed universe must be finite in size, a perfectly flat, uncurved universe can stretch out infinitely, extending across an absolute eternity of space. If this is true, The 93 billion light-year sphere of our observable universe is not a substantial portion of the whole cosmos. Instead, it is an infinitesimal, microscopic fraction of an infinite landscape. To understand how the universe grew to be this incredibly massive while remaining so perfectly flat, cosmologists formulated a revolutionary scientific concept known as the cosmic inflation theory. Development in the late 20th century by physicists like Alan Guth, cosmic inflation describes a monumental event that occurred during the very first fraction of a second of the Big Bang, specifically between 10 to the minus 36 seconds and 10 to the minus 32 seconds after the initial singularity. Before this era, the infant universe was a microscopic patch of energy far smaller than a single subatomic proton. Inside this ultra-dense quantum state, all parts of the infant cosmos were in direct physical contact, allowing the temperature and energy to smooth out perfectly. Suddenly, a mysterious scalar field drove a period of exponential runaway expansion. During this unfathomably brief interval, the fabric of space stretched outward at a speed that vastly exceeded the absolute speed of light limit. Space expanded by a factor of at least 10 to the 26th power, instantly inflating a subatomic patch of space into a macroscopic realm spanning light-years across. This cosmic inflation perfectly explains why the universe appears so completely flat to our modern instruments today. Imagine an individual standing on the surface of a small, bumpy balloon. They can easily detect the curvature and irregularities of the rubber surface. However, if that balloon instantly inflates to the size of the entire planet Earth, the local surface will appear perfectly flat to the observer, and the distant curvature becomes completely imperceptible. Cosmic inflation took the tiny, smoothed-out quantum fluctuations of the subatomic infant universe and stretched them across macroscopic space, creating the massive density seeds that would eventually grow into the dark matter filaments, nodes, and voids of the cosmic web. This means that the gargantuan structures we map today, the filaments of Laniakea, the massive voids of Boötes, are simply the magnified imprints of subatomic quantum mechanics written across the sky. Crucially, the process of inflation was so violent and rapid that it pushed the vast majority of the newly created space far beyond our observational horizon. The region of space that inflated during that initial second is vastly larger than the small bubble we can see today. Astrophysicists have used the mathematical constraints of inflation and flat geometry to estimate the absolute minimum size of the full universe, including the unobservable regions that sit past our particle horizon. The calculations reveal that the unobservable universe is at least 250 times larger in linear diameter than our observable bubble. This means that if the observable universe is represented by a small glass marble measuring 1 inch across, the full universe would be a massive sphere stretching wider than the entire planet Earth. And this is merely the absolute minimum boundary dictated by our current measurement limits. The true universe could be infinite. This expansion of our scientific perspective fundamentally deconstructs the scale of the Milky Way. Our home galaxy, which already felt completely insignificant inside the 93 billion light-year observable bubble, becomes entirely lost when placed against the backdrop of the full universe. We are talking about a physical architecture where the entire observable universe, with its 2 trillion galaxies, its trillions of stars, and its immense expanses of dark matter, shrinks into a solitary random atom inside a planet-sized structure. Every single thing humanity has ever detected, every physical law we have ever written, and every deep space image we have ever captured represents a microscopic sliver of an uncurved expanse that stretches across quadrillions of light years. The science of the final frontier proves that the universe is defined by scales that mock human ego and challenge the absolute boundaries of our mathematics. The Milky Way is a tiny, beautiful citizen of an unobservable empire that expands continuously beyond the reach of light itself. As we stand on our small planet and look out past the stars, we must accept that the true scale of reality is not just vast, it is an infinite expanse of flat space, born from a subatomic quantum flash, stretching out into permanent darkness that human eyes will never see. Having established that our flat universe could extend infinitely far beyond our 46.5 billion light-year particle horizon, The laws of physics and mathematics force us to confront an even more mind-boggling possibility. If space is truly infinite, then the collection of matter and energy we call our universe is not all that exists. Instead, we must explore the mathematical framework of the multiverse hypothesis. On this grandest possible scale of cosmic progression, the Milky Way galaxy completely vanishes from the equation, and even our entire 93 billion light-year observable bubble shrinks into a solitary subatomic particle floating inside an infinite ocean of parallel realities. The first layer of this cosmic concept is rooted in the simple mathematics of infinity, classified by cosmologists as a level 1 multiverse. Imagine an infinite universe filled with a uniform distribution of matter and energy, just like the flat space indicated by our measurements of the cosmic microwave background radiation. Within any given observable bubble of our size, there is a finite number of subatomic particles, specifically protons, neutrons, electrons, and dark matter particles. Quantum mechanics dictates that these particles can only be arranged in a finite number of distinct physical configurations before the patterns must mathematically repeat. The total number of ways to arrange these particles is a monstrously large number, calculated as 10 raised to the power of 10 raised to the power of 122, but it remains a finite number. In an infinite space, the laws of probability state that every single possible configuration of matter must occur somewhere, and it must occur an infinite number of times. This means that if you travel far enough into the unobservable universe, past the boundaries of our local flat space, you will eventually encounter another observable bubble that looks exactly like ours. You would find an identical copy of the cosmic web, an identical copy of the Laniakea Supercluster, and an identical copy of the Milky Way galaxy. Within that duplicate galaxy, there would be an identical copy of our solar system, an identical Earth, and an identical version of you reading these exact words. The mathematical distance required to find such an identical twin universe is estimated to be 10 raised to the power of 10 raised to the power of 29 meters, an incomprehensible distance that highlights the sheer power of infinity. But modern astrophysics pushes past this geometric infinity into an even deeper layer of the multiverse, known as a level 2 multiverse. This model is a direct mathematical consequence of combining the cosmic inflation theory with quantum mechanics, a concept known as eternal inflation. As we discovered previously, cosmic inflation drove a period of exponential, runaway expansion during the very first fraction of a second of the Big Bang. According to the mathematics of eternal inflation, this rapid stretching of the space fabric never actually stops everywhere at once. Instead, the scalar field driving inflation continues to expand space eternally across the macroscale of reality. However, quantum fluctuations cause inflation to naturally decay and drop in localized pockets of space. When inflation stops in a specific region, the intense energy of the scalar field instantly converts into matter and radiation, triggering a localized Big Bang. This pocket of space settles down into a stable, slowly expanding universe, creating a self-contained cosmic bubble. While our local bubble grew to become the 93 billion light-year observable universe we map today, inflation continues uninterrupted in the vast space surrounding us. This eternal expansion continuously drives the empty space between bubbles apart, at speeds far exceeding the speed of light, ensuring that individual pocket universes can never touch, interact, or communicate with one another. This creates a spectacular image of the cosmos on a truly grand scale, an infinite, violently expanding ocean of inflationary space, populated by countless separate, isolated bubble universes. Each individual bubble universe is born from its own distinct Big Bang, experiencing its own era of recombination and developing its own unique configuration of dark matter filaments and galaxy clusters. Crucially, the laws of physics themselves can vary from one bubble to the next. The precise mass of an electron, the strength of the gravitational constant, and the total density of dark energy are determined by the random way the scalar field decays within that specific pocket. In some bubble universes, gravity might be too strong, causing the entire pocket to instantly collapse back down into a singularity. In others, dark energy might be too aggressive, ripping matter apart before stars can ever ignite. When we view reality through the lens of the level 2 multiverse, the scale of our existence undergoes an absolute paradigm shift. We began our journey by measuring the Milky Way galaxy, a structure that spans 100,000 light-years and contains hundreds of billions of suns. We saw how this massive stellar metropolis was swallowed up by the Virgo Supercluster, Laniakea, the cosmic web, and the 46.5 billion light-year radius of the observable bubble. Now, the mathematics of physics reveals that our entire observable bubble is merely one tiny microscopic drop of water inside a single bubble universe, which is itself just one solitary bubble drifting in a boundless, eternal multiverse. The multiverse theory represents the broadest scale considered in modern cosmology. It proves that the scale of the universe is not just vast in terms of physical distance, but infinite in terms of structural variation and potential. The Milky Way is a tiny, beautiful citizen of one specific cosmic island, governed by a unique set of physical constants, floating in a limitless archipelago of realities. As we look past our stars and confront the mathematical inevitability of these distant bubbles, we must accept that our galactic home is not a dominant centre of existence, but an infinitesimal spark of light within an infinite, unfolding masterpiece. Our journey across the deep cosmos brings us back to the absolute centre of our observational reality, standing on a tiny rocky planet orbiting a mundane star within the suburban branches of the Milky Way. We have traced a monumental path of cosmic scales, climbing the distance ladder from the geometry of stellar parallax to the blinding brilliance of Type 1a supernovae. We watched our home galaxy, with its 400 billion suns, shrink into a single grain of sand within the local group, only to see that neighbourhood swallowed by the flowing gravitational currents of the Laniakea supercluster. We observed the majestic, fibrous architecture of the cosmic web, where entire superclusters are merely minor threads, framing gargantuan voids of absolute nothingness like the Boötes Void. We confronted the mathematical paradox of our 93 billion light-year observable bubble, shaped by the expansion of space and illuminated by the ancient microwave background radiation. Finally, we ventured past our particle horizon, uncovering a perfectly flat universe that stretches across millions of light-years, potentially existing as a single drop in an infinite ocean of eternal inflation and bubble multiverses. When confronted with this staggering architecture, it is easy to succumb to a feeling of total cosmic insignificance. On a purely physical scale, the Milky Way is an invisible atom, and human life is a fleeting subatomic whisper in a cold, expanding dark driven by dark energy. Yet the true miracle of the universe does not lie in the physical scale of its massive structures or the terrifying volume of its empty voids. The true miracle resides right here on this small blue world. We are a collection of normal matter, born from the hearts of ancient exploding stars and gathered by the invisible hands of dark matter, that has evolved the capacity to think, to observe, and to calculate the universe that created it. Humanity, operating from a tiny galactic outpost, has managed to decode the laws of general relativity, map the boundaries of Laniakea, and build golden mirrored telescopes capable of looking backward through 13 billion years of time to see the first generations of starlight. We are the universe experiencing itself, a conscious bridge through which the cold vacuum of space achieves self-awareness. Our capacity to comprehend this vastness is the ultimate triumph of mind over matter. As we gaze out at the eternal night sky, we recognize that while our galaxy is beautifully small, our connection to the cosmos is absolute, proving that the mind of the observer is just as miraculous as the infinite universe it seeks to understand.